Episode 93, Nobel Laureate in Physics and Senior Project Scientist in the James Webb Space Telescope, Dr. John Mather. Welcome to The Art of Excellence, a show about people doing extraordinary things in their lives. I'm your host, Glenn Zweig. Thanks for joining me. My guest today is John Mather. John is a senior astrophysicist in the Observational Cosmology Laboratory at NASA's Goddard Space Flight Center. He is also the senior project scientist in the James Webb Space Telescope. His research centers on infrared astronomy and cosmology. He was the chief scientist for the Cosmic Background Explorer and received the Nobel Prize in Physics in 2006 for his precise measurements of the cosmic microwave background radiation. He has served in advisory and working groups for the National Academy of Sciences, NASA, and the National Science Foundation. Well, John, welcome to the show here.
Thank you. Good to be here.
It's good to have you. So John, here's my simple request for this interview. I promise you, I give you my word, you will not insult me if you dumb it down. So, kidding aside, feel free to treat me like a fifth grader. I'll let you know if we have to take it up to a seventh or eighth grade level. I will take my chances on losing the one or two astrophysicists in the audience. But does that sound good?
Yeah, I'll do that.
Fantastic. Just because it's top of mind, I want to start actually with the James Webb Telescope. Just launched into orbit last year. It's been releasing these stunning images. And just the other week, it detected its first exoplanet, which, as I understand it, is a planet orbiting another star. It's about the size of the Earth. It's called, here comes a really catchy name, LHS 475b. And it sits 41 light years away, which I guess is somehow close in relative terms. I was curious, what makes this discovery, this exoplanet, so exciting?
Well, number one, it's the first one that we checked up on that we didn't already know was there. So that's why it's a kind of discovery. We had suspicions that it was there. Mm-hmm. So the way that we do it is we watch a star and we see if it blinks when a planet goes in front of it. And so this one did. So now this new equipment was enough more powerful that we could tell for sure.
But the fact that it's an exoplanet, I don't know, is this something where, because it's an exoplanet the size of Earth, I think it may be mountainous or something, as I recall. Is that anything that might give us some hope that there could be life? Is that the point of it?
Well, we're just really at the beginning of looking for planets that are like Earth. So we have a long catalog of planets that are going around other stars, about 5,000 of them. So the question is, are any of them at all like Earth? So what would it be like to be like Earth? It needs to be about the right size, about the right temperature. And then if we're lucky, we can tell if it has an atmosphere that would tell us that it could even be an ocean there. So that's what we're up to now, is we're beginning this search for Earth-like planets. The ones that we are aware of that we can study well are orbiting stars that are not like the sun. They're much smaller and cooler and rather hostile. So in the sense that they send out blasts of magnetized plasma that could rip the atmosphere right off a planet. So if that's true, then those are really not likely to be like Earth. But they're where we get to start because that's what we can work on today with the equipment that we have.
I also read that it's given us a way to measure the coldest ices within molecular clouds, and that these molecular ices are somehow the raw ingredients, as I understand it, needed to form stars and planets. Can you explain that one a little bit?
Yeah. So the question that we have is, well, how come Earth has volatile elements on it? Like water, some of the metals are a little bit volatile. You get the planet warm enough, they'll all evaporate. So we picture the Earth forming out of a lot of collisions of little hot rocks when the sun was quite young, and So the question would be, how come we have any water, since it would have all evaporated? So now we want to know, where did it come from? And it could come from the outer solar system, where it was colder when the solar system was young. And even before that, what was it like before the solar system was forming? So we see with the Webb telescope places in outer space where stars are just beginning to form. And we can see that there are clouds that have solid materials. And we can begin to tell which molecules are in those solid materials. Some kinds of ice, not just water ice, but ice that has other materials in it, like ammonia or carbon dioxide or carbon monoxide. They're all interesting because they tell us what was there before there was a solar system. Of course, by the time we get to having an Earth, everything's been melted and scrambled. So they're not really the building blocks of life, but they're the raw materials that will be scrambled up to make life. So that's why we care.
Wow. So are we, I know we're in, chapter one, of a 100-chapter book. I think this is meant to last 20 years or something out there in space. Are we already starting to learn what you were hoping that we would learn from this? Or like, was there even a specific, I guess, agenda in terms of these are the kinds of questions we hope to, seek answers to?
We had, starting off, lots and lots of questions, but we distilled them down to four main ones, which is, well, what happened after the Big Bang? Where did the first things grow from? So the Big Bang gave us hydrogen and helium and some small variations of density across the early material. And then what happened? Somehow we got stars and galaxies. So when and how? That's the big question. So we wanted to know this from the Hubble telescope, and we couldn't find out because the Hubble couldn't see far enough back in time. So, okay, look at that. What's the first thing that happened? And was it black holes first, or was it galaxies first, for instance? Then how did the galaxies grow? The Milky Way was probably assembled out of thousands of little pieces. Well, how did that happen? Then how are the stars being born today? So we couldn't know that in the past very well because it happens inside clouds of dust and gas, which are kind of opaque. When you have the Hubble telescope, you get a nice sharp view of a cloud. And so you can't see the stars inside the cloud very well. So the Webb has infrared capabilities that let us see through the dust, inside the dust cloud, to see the stars being born and see those molecules and ices that we're talking about. Finally, what about planets? How did the planets grow? And what are they like? Are any of them going to be like Earth? So all of those four main questions are driving the design of the original observatory. And then we build something as powerful as we can and see what we can see. So now we're pointing it at everything.
John, I know you're a scientist, and generally speaking, scientists need, hard evidence to have any kind of confirmation. But in your gut, do you believe there is some form of extraterrestrial life out there?
Yeah, I do. We don't have direct evidence, but we do have some evidence from the one place we know about, which is right here on Earth. That is that the fossils are telling us that soon after there were oceans, there were fossils. So within a few 100 million years. Well, okay, then maybe the formation of life is not require a very rare and exotic coincidence. Maybe it's something that always happens given the chance. So that's my gut feel. I think that's the evidence we have from the geology. So now, are there other places that could have this kind of geology? That's our next astronomy question. Are there planets that are enough like Earth to have an ocean with all of the chemistry going on that we have? So are there conditions somewhere that life could occur? Well, my gut feeling is, well, the universe is extremely large, probably infinite. So that means even things that are pretty unlikely and rare will turn up somewhere. So the thought that I have is life is surely out there, but the neighbors are probably not very close by. So it's going to be hard to find them. Of course, we've been listening with our radio telescopes for many years, hoping somebody's sending a signal, but now we haven't picked up anything. That's intelligent life with high technology. But ordinary life, algae, bacteria, single cells, well, that happened really quickly here on Earth.
So I want to rewind the clock on you, if we could. So you grew up on a farm, and your dad was researcher studying farm animals. Did you enjoy farm life, or were you bored out of your mind?
Well, I actually wasn't a participant in the farming. I lived in the house and I went to school and I studied science from books and played with science toys and made my little telescopes with cardboard tubes and lenses and had a radio kit. I put together a radio from a Heath kit. So all the things that a kid did in the 1950s and 60s to begin to get into science, that's what I did.
And it probably didn't hurt that you're in this. I assume, obviously, you're on a farm. You're in a very rural area, away from urban lights, which would generally impede stargazing. So probably made it really easy to catch some things that intrigued you. Do you remember like what you found so fascinating?
Well, I do remember that it was the sky was interesting. There was some comet that came by when I was a kid, and I thought that's interesting. There's stuff going on. You could see the stars quite well. My dad bought a telescope from Sears Roebuck. We looked at Mars, and it was pretty clearly not a good enough telescope to tell much. So needed bigger, better one. We went off to the Museum of Natural History in New York City to see the planetarium show, and I loved it. And there's this giant meteor, which is about as big as a living room at least, and it's sitting there next to the planetarium, and you say, how did that happen? So when you're a little kid, you want to know. And so I still want to know.
It's the Hayden Planetarium, yeah.
Yep.
And I read that you visited it when you were 8, and that's what sort of ignited your early passion for astronomy. Is that right?
Yeah, that's the part I remember.
Yeah. Do you know who else visited the Hayden Planetarium and had their passion ignited? Neil deGrasse Tyson. He was 9. You were 8. You got the bug 1 year earlier than he did, but that's I should have visited the Hayden Planetarium. Maybe I'd be doing something different today. But it clearly was very inspirational.
But also the museum with the dinosaur bones and the volcanoes and all the stories about the history of Earth that are just sitting there, and you say, how did that happen? How did that happen? I just want to know everything.
Yeah, you're very curious. What I thought was interesting is you weren't just interested in science per se, or astronomy or cosmology, but specifically making instruments. Like the telescope you made out of a mail order kit. So was that something early on that you weren't just fascinated as a kid, but you sort of set your sights on this being a future career? Like when did that actually come into reality that this is the rest of your life?
Well, it's hard to tell exactly, but I know by the time I was in high school, I already knew that it was an exciting subject and that I was pretty good at science. So I knew there was a possibility. You never know whether you're going to be able or whether the world will cooperate with your wish. But it was a time when suddenly the USA was terrified of the Soviet Union. We were going to get nuclear bombers and all kinds of stuff. And then Sputnik went up. So suddenly there was a lot of public support for young kids like me to go learn science. So, okay, so the opportunities felt open. But my career has actually been a little chaotic in the sense of it wasn't the way I planned it to be. I didn't really have very much of a plan. But when somebody said, would you like to try this? It's interesting. I said yes. So that's how I ended up here. I said yes to opportunity when it turned up.
Yeah, you sure did. Well, I want to fast forward through school onto your PhD. The thesis project was studying ways to measure what's called cosmic background radiation. It had been a relatively recent phenomenon that had been discovered, I think. So just to start, can you explain what exactly is cosmic background radiation?
Well, back in 1929, Edwin Hubble drew us a graph that said the universe is expanding. All the galaxies are rushing away from us at tremendous speeds, more or less proportional to distance. So, okay, the universe has an age. Divide the distance by the speed, you get the age. Now imagine running the expansion movie backwards in your mind. The galaxies are mushed together. Well, is that going to be hot? Probably. So what was the universe like when it was young? Hot and dense and very compressed. So what's left of it now? Well, the heat radiation that was there then should still exist. So that was predicted in 1948. It was discovered more or less by accident in 1965. And then in 1970, I was a graduate student looking for a thesis project. And so, well, let's go try to measure that radiation from the ground a little better than it had been. Okay. And then that worked, but not very interesting. So, how about a balloon payload to measure it better? So, my thesis project was designed by my advisor. And so we built it, we launched it. It did not work. So, I got to write a thesis about a non-working apparatus.
John, didn't you try? There were a couple of techniques, right? Didn't you also try something on a mountaintop or something like that?
Yeah, we did the mountaintop experiment, and that one worked. It was hard work too, but anyway, so I managed to leave graduate school with a thesis. It was not a bad thesis, but I was discouraged about this subject, so I thought, oh, I probably won't work on that anymore. And I got a job at NASA in New York City. There's a Goddard Institute for Space Studies there. And so I was sitting there thinking about radio astronomy when NASA called for proposals for new satellite missions. Okay, this 5 years after the moon landing. Okay, well, hey, boss, my thesis project failed, but we should try it in outer space. And he knew that that was right. So we called up our friends, we wrote a proposal, and that became the Cosmic Background Explorer satellite, which became the thing that measured the Big Bang very, very well. We measured that cosmic microwave background radiation, and we confirmed that it has the right color, which is to say no color. It's a very simple formula for how bright it is. And we also measured that it has hot and cold spots. It's not the same exact brightness in every direction. We knew that they had to be there, or we couldn't explain how come there are galaxies. But nobody knew much. There was no fundamental prediction that it had to be there. Our job, we're scientists, we just go measure. And so we measured, and there it was. And it's turned out to be extremely, extremely important for cosmology.
Well, we're going to get into some of this here, but just to back up for a minute, we've all got, I think a concept, a very, very surface level concept understanding of the Big Bang. But I want to hear you explain it. Help me understand what is behind the origin of this expanding universe.
Oh, okay. Well, I sort of go at it backwards. I say we see the universe is expanding. We see that it's extremely large. We can't see to the edge. So imagine running the movie backwards in your mind. As we said earlier, you get to hotter and denser, and things are mushed until they're no. And if you push it far enough back, they're no longer even any atoms. They've been ripped apart. Okay, very, very hot, very, very compressed. We call this initial condition, whatever it is, the early conditions, the Big Bang. We're a little uncertain about what exactly we mean by the Big Bang. One way to say it is when we run out of imagination and we have no idea what is the right description, then we call that the Big Bang. But everybody wants to know, well, before there were atoms, was there something else? Mm-hmm. And the current offer is something called inflation, cosmic inflation. So it's been imagined that the early universe was filled with a special quantum mechanical substance called inflation field, and that it was unstable and caused expansion of the universe, and then turned itself into atoms, to the particles that make up the atoms. So that's kind of wild and weird, but it seems to match the observations. So this is something Alan Guth told us about quite a few years back. So that's the sort of predominant current theory about what happened before the atoms existed.
I'll try to wrap my my head around that. I'll be processing that for a while here. John, what I thought was really interesting is, and this isn't me opining, these were sort of, your words, where, society holds the theorists like Einstein, who can create a formula that ties everything together in much higher regard than experimentalists like you. But, that never seemed to deter you. You always love building things, tinkering with things, helping us understand how to see the world in a new light. Was that never something that you thought, I'm going to devote my life to something that maybe is, at the time, obviously you ended up winning the Nobel, but at the time maybe underappreciated versus other areas in astrophysics and cosmology?
Well, I don't know. I just have different viewpoints than other people do. There was a long time that I wanted to be a theoretical physicist. Like Richard Feynman was one of the most famous. I thought I'd like to be like him. But I asked around for advice in graduate school, and they said, "Are you rich? There are no jobs for those people." Okay, so I'll try something else. I'm interested in building things. I always have been interested in building things. So I always felt, even from the beginning, that we discover things when we make new equipment. We make a microscope, we make a telescope, we make a particle accelerator. We learn something that nobody else could have known before because we built something. That's been my sort of strategy for success, is to build something, to learn something. So theorists build something too. They build a theoretical construct. It may not look like brass and screws and bolts and things like that, but it's something they've constructed. But some of us just really like the hardware, so I do.
Well, let's talk about building this COBE, they call it, right? The Cosmic Background Explorer. So it took from idea to launch, it took 13 years.
Actually, a little longer. It was 1974 proposal to 1989 launch. So, yep.
So I'm off by a couple years. So 15 years. Was this more about technology limitations, or was this more about politics and other issues that had to be resolved?
Oh well, I think it's just that there's an awful lot of steps along the way. When you start off, you just have a little thin proposal that says, "We think we could build this." And then the next step is we work with engineers to say, yeah, not only we think we could, this is how. And then we say, but we don't have this and that. We need to invent better detectors. We need to design a cooler. We need to figure out the orbit. We have to figure out how we're getting into space, which launch vehicle. All those things have to be worked out. And then after you've figured it out, which is quite a few years of discussing, arguing, drawing, planning, then you say, okay, we're ready to go. Will somebody please approve that this is a thing that we should do? So that's what NASA used to call a new start. It was approved by Congress at a certain point. So it takes a while to get from idea to approval and then you start building. And then, and of course, it's harder than you could ever have imagined. And then we had another thing happen. Of course, we were going to be launching it on the space shuttle from California. And then the Challenger blew up, and people never did launch a space shuttle from California. So we had to change the plan. We had to rebuild it or launch on a Delta rocket. So that's part of the story of how it takes a long time, and things that you can't imagine that are not under your control change your world. But because people knew right away from the very beginning that this was really important, then people supported all the necessary extra work.
So you mentioned how during your PhD project, when one or two of the experiments didn't work, how it was a little bit discouraging. And here you are in a 13-year endeavor with a lot of ups and downs along the way. How do you stay motivated, John? How do you keep your team motivated? Were there times where you said, okay, it's just not meant to be, let's move on to something else? Walk me through some of that.
I never felt dark about it. I never thought, even after the Challenger loss and we knew we had to rebuild, I never felt dark. I just thought, we have the most exciting thing we could possibly be working on right now, and we'll find a way. And so people did.
Well, of course, it did get launched, and it gave you the data that you were looking for. So did this data essentially confirm, and maybe that's the wrong word, the Big Bang, or did it just get us closer to validating that there's such an event that happened? Help me understand sort of the implications for the measurements that this project did.
We did two things. Number one, we measured the color of the heat radiation. So there were alternative theories. There was one called the steady state theory that said the universe has not only infinite in size, but infinite in age. So what they thought would happen would be stars would be producing energy and it would be converted into millimeter waves by dust grains. Okay, so they could not match the measurement that we made. So, okay, so that theory is dead. There were other versions too of the expanding universe story. What if it was cold when it started? Well, how could you tell? So that was the sort of number one thing. There was no significant alternative to the expanding universe story. Then a couple of years later, we got the hot and cold spots and said, okay, that explains how come we're here. That was a big mystery until then, because if the universe had been completely exactly uniform when it was young, gravity wouldn't know which way to pull. It would pull equally in all directions. So it would just continue to be completely uniform forever. And there would be no stars and galaxies. So from that logic, you say there have to be hot and cold spots. And then when we found them, it was a hugely important discovery. And Stephen Hawking called it the most significant scientific discovery of the century, if not of all time. Yeah, okay, well, at first I thought, well, Steve, that's just really nice that you said that. And now, since I just told you the story of why it's so important, it's more than that. He was right.
Were you and Stephen Hawking close? Did you know him well?
I met him a few times, but I didn't really know him well.
It was 2006 when that work that you did finally won you the Nobel Prize in physics.
Mm-hmm.
I know I can tell you're, a very modest person, but as you were embarking on this endeavor and continuing for years and years and years to see it through, were you ever thinking that this, if we learn what we hope to learn, if we can capture the measurements, this could be something so big that this could be the kind of discovery, if you will, that could earn the Nobel?
Yeah, I knew that. I knew that from the beginning. People around me said that too. I wasn't the only one with that hope.
Mm-hmm.
By the way, on the subject of modesty, my wife said she'd never seen the slightest sign of it. It's also very important to know that being smart doesn't do anything because you're working with a team. And so we moved together as a team. And so every day when I would go to a meeting that I was running, I would say, I don't know the answer to this. I don't know the answer to that. Who here knows the answer to this? And so that's actually my secret to success is not knowing, but asking.
That's actually really interesting. Has that sort of been a theme throughout your career?
Yeah, that's sort of my personality. There's always somebody in the room that knows something that I don't know. And if I try to do their job, that's terrible. So I should help them do their job by asking questions and supporting their decisions and their opinions and their discoveries so we can work on something together.
I mean, it's so obvious it's the right thing to do, but there's a lot of people out there who don't because they feel it's a sign of weakness, of vulnerability, of not sort of being on top of the knowledge they need to be leading a project. But that speaks volumes that, you can do that.
Well, I think if you already know that you know what you're doing, then you don't have to persuade people that you know what you're doing. You just have to do it. In the case of project leadership, then it's making sure everybody else gets to do their part.
Yeah. Did winning that Nobel change your life in any way?
My resolution was to not let it change much. So I kept on doing the same job at NASA. I got a lot of invitations to travel and speak, but I was already doing that. So I thought, well, this doesn't mean I'm a different person. It just means everybody wants me to do something new. Stick to what you're good at. That was my plan.
Well, you could have gotten that Nobel and said, it's been a great career. That's been fun. Let me retire. Let me go teach. Let me go have the easy life. But then it's not often I interview people that have had two gargantuan feats, that being the first, and of course, then the James Webb that we already started dissecting. Was this something that you would set your eyes on, or did someone find you? Was this serendipitous how you found your way into this project?
Well, this is one of those curious things. I've been thinking about what do we do for the next telescope after the Kobe satellite was finished. I'm thinking, well, we're never going to do anything that exciting again. Do I need to become a professor or something? And one day I found this phone message from the boss at headquarters that said, we're going to start studying this new telescope. Do you want to work on it? Oh, man, I do want to work on this. It's the most important thing I could imagine working on. So yes, absolutely. So I dropped everything else that I had in mind and said, yes. So that was the fall of 95. And so it's been that project ever since.
So you had sort of mentioned earlier that it's infrared, which is something new. Hubble was not. This mirror, 21 feet in diameter, which I think is 3 times the size of Hubble's. Well, the James Webb took 15 years, we said. This one took 26 years from concept to launch. Would love to understand what was behind, 2.5 decades in the making. But also, if something takes that long, I mean, heck, back in the mid 90s, the iPhone didn't even exist. So is it that you're waiting for certain technologies to come into existence or get to the right price point? Because whatever you're starting to think about of how this comes together, 25 years ago changes every few years.
Yeah, so we should take out the word waiting because there's no such thing. We're not waiting, we are pushing. So when we say we want to build this telescope, we make out a list of the things we need to invent that we don't have. We think we could get them to be this good, and so now we need to push. So, okay, world, tell us how you would build a mirror, how you would build the better detectors, how you would build the cold electronics, how you would unfold the telescope, all the things that we have to learn how to do before we can promise we can do them. So we set out competitions. Okay, world, prove to us that you could build a mirror. And we had altogether 12 contracts with companies that said they could build a mirror. And only one of them was actually good enough. So, okay. So we're not waiting, we're pushing. So that means that we have the best available technology in the machine because nobody was making it before us.
Were there 2 or 3 key technological breakthroughs that were needed for this to come to fruition?
The ones that looked hardest were number one, how do you focus the telescope after launch? Because we had launched the Hubble and it was not in focus. Oh man, that was a problem.
Forgot about that. Yeah.
We had to go rescue the Hubble with an astronaut mission and fix that all. Number two, how do you make the mirrors? Because they have to be much bigger than Hubble's mirrors and much lighter because the rocket that we needed couldn't push the telescope out there if it was nearly that heavy. So the mass of Webb is about half the mass of Hubble, but we had to push it much farther out, 1 million miles farther. So, okay, that tells you what your job is. You have to make an ultralight, extremely good mirror that can be focused after launch. Okay, well, this is hard. But people have plenty of ideas, so we just have to work through them and sort them out until we get one combination that works.
And as I understand it, it wasn't just about being a daunting technological feat to pull off, but it was as much about how to make this thing operational in space. The fact that it had to be 1 million miles away, the fact that this had to open itself up, the fact that you needed some sort of shield to protect it from the elements because it has to be at a certain cool temperature. Can you talk about some of just to operationalize it, even once you have the technology of the telescope, just to get it out there so you can have a 20-year operation?
So the general idea is pretty clear. You build it and you unfold it in space. But when you say unfold it in space, there's a lot of magic that's required practically because you can draw it and you can build it and then it won't work because there are too many things. It's too complicated. So for the big sunshade that unfolds, it has 5 layers altogether. It has to be folded up like accordion pleated so that the air can get out from between the layers when you launch. And then, you're not going to have any second chances because you can't go out in there and fix it. It's too far away. Okay, so rehearse, practice, rehearse, practice. We actually unfolded it 4 times to make sure that it would be ready for launch. And all 4, there was something that wasn't quite right. And the last one, however, we said it's close enough. And we fixed the little things that were still left over. And then, okay, we're pretty sure it'll work this time. And we were right. But it's extreme attention to detail that's required for something like that. It's a little bit like packing your parachute. You know how to do it. You'd better darn well do it the same way that you did it before, the last time. Then, it's so complicated. After you've got it up there and it's unfolded, now what you're going to do? You got 6 months to get it all set up and working. And in particular, how are you going to rehearse that so it works right? So we built ourselves what I call a digital twin. a simulator for the actual operation of the whole observatory.
Hmm.
So it's a computer program that behaves like the real thing. Send it commands, it takes pictures, sends back data. And so everything is rehearsed and practiced for years before the launch, so that when you actually get your chance, it'll work right. And it did. We were within a few days of the planned schedule for getting it all unfolded and ready.
And when those first images started coming in, was it a similar feeling to when you started getting the measurement data back from the Kobe project?
Yes. Well, I knew it would work, but nevertheless, seeing it in real life for the first time is spectacular, because the first real picture that we all got to see together was a proof that it was focused. You know, the focusing was the hardest part. Make this little star look like a dot. And we saw immediately this little star that looks like a dot with spikes sticking out is surrounded by galaxies. They're just everywhere. They called it, we were photobombed by galaxies. But they're just everywhere. So we knew everyone could see the very first picture we got was spectacular.
I mean, one could spend the next 20 years studying these images and starting to dive deep in terms of the questions that have been lingering for so long that we might start to crack away at. But I know you said earlier how you chose the path of tinkerer, not theoretical physicist. So are you already on to your next James Webb out there, or are you able to sit back and say, I'm going to just spend a couple of years immersing myself in some of the data that we're getting back?
Okay, well, what interests me is the next telescope. It's what my mind has been working on all along. We see what we did with this one. We see what was hard about it. We always have ideas about if I build my next one, I'll do it differently and better. So actually, the National Academy of Sciences told us what they want us to build next. And it's called the Habitable Worlds Observer. So it's at least as big as the Webb and much more accurate, which means that we would be able to see an actual image of a little Earth separate from the star that it's orbiting around. So then you can say, okay, now I can see this could be like home or not. Does it have the colors of Earth? Does it have the chemicals that Earth's atmosphere has? Does it spin like Earth? Is it anything like Earth? And so we've got, of course, a list of nearby stars that are like the sun, and we know that most stars have planets. So we got a good shopping list of places to go and see what's out there. So this is the most difficult observing program that astronomers have ever imagined. And so we're going to try it. So I want to work on that.
Wow. So is that a project that's already funded, or is that in the research phase, or where is that at?
It's at the very concept stage, because right now other projects require the money to get them finished. The next one NASA's flying is called the Nancy Grace Roman Space Telescope. And it's going to be doing a sky survey, looking for signs of cosmic dark energy and cosmic dark matter, and also hunting for planets around other stars. So it's coming first. But we're just collecting our ideas. What are we going to do for the one after that one? Hmm. And I have some other ideas that are called hybrid observatories. So we've got telescopes here on the ground. And what if you could put something in space that would help them work a lot better? So I've got some ideas in that direction.
I think I read about that. Somehow to dim all the excess light that's coming from the stars that's impeding our ability to see the planets.
Yeah, that's the wildest that's the most difficult of these ideas. But the telescope they're building now in South America, it's called the Extremely Large Telescope. It's got a diameter of 39 meters, which is over 120 feet or something. Wow. It's enormous and is so much bigger than anything we can put up into space anytime soon that, well, what if you could use it to see planets? Yeah, okay, meaning planets around other stars. Mm-hmm. And what would you have to have? You'd have to have either a perfect optical system that could block the starlight inside the telescope, or alternatively cast a shadow of the star onto the telescope so you could see the planets next to it. So that's called an orbiting starshade, and that's what I've been working on.
Hmm. So, you mentioned earlier how your ability to show humility by asking questions, to surround yourself with others that have a lot of knowledge you may not have, and this has been, an element of your success. What else, if you look back and reflect in terms of what's behind, and I know it's a team effort. I get it's not just about John, but you were an integral part, in both these projects. What else would you attribute the success to?
What do I think leads to success? Well, number one, it's curiosity and playfulness. We don't just drive hard for an objective. We have to sort of keep our eyes open for what's nearby, what's another branch path. It doesn't work real well to just be too fixed on a single objective if you're trying to explore the whole universe. You'll miss something. So my strategy has been to talk to people and say, what's interesting? What are you working on? Maybe we've got an idea together. So a lot of my most creative thoughts have come from conversation with other people. Okay, I think that's a good strategy, talking with people. Our readers, our listeners might think, well, scientists work alone, but actually we are hypersocial. We do everything with each other. Charles Darwin's Origin of the Species book is just page after page of I talked to this person, I wrote to that person, I got this idea, I have this evidence, because this is basically, he's telling you he's a connected scientist. He's working with everybody. And so that's our scientific world like that these days. We're always talking to people. So there's plenty of things to work on and challenges that are beyond imagination. I'm going to a conference, video conference shortly on what's the next even bigger telescope that we could build on the ground. We love being imaginative.
Yeah. Was there anyone over all these years, or maybe more than one person that served as a North Star to you, someone you admired, whether another scientist or someone else that sort of kept you motivated?
Well, the three most recent people that made big differences to me were my thesis advisor in Berkeley, Paul Richards, my postdoctoral advisor in New York City, Pat Thaddeus, and then the man who hired me at Goddard, Michael Hauser. So these three people all showed me what it was like to be a good scientist and a good human being. And so I try to do what they do, learn by example. I don't try to imitate people. I think that's too hard, but you just learn to do what they do.
Yeah. John, the name of this podcast that you've been speaking on is called The Art of Excellence. And I always enjoy wrapping up with asking my guests, when they think of the word excellence, what do they think of? What comes to mind?
Well, to me, it's more like doing the best job you can possibly do. The word literally means to be beyond something else, maybe to excel over other people. But I don't take it that way. As a scientist, my job is to solve cosmic problems. And our challenge is to work with the unknown. So that's where I think the challenge is. I'm not trying to beat somebody. I'm trying to be a part of a community that discovers something together.
It's a brilliant answer. Well, this has been, I could spend another hour easily, but I don't want to keep you. This has been fantastic. I know we barely scraped the surface. So much more for me to learn about this, but thanks to you and thanks to your team and tireless hours, years, decades working behind it, and can't wait to hear more about this next project you're working on, John.
Well, thank you, Glenn. It's a pleasure talking with you, and look forward to hearing the podcast. So you'll send me a link to it, right?
Absolutely. Thank you, John. Really enjoyed it.
Okay, thanks. Bye-bye for now.
Hey, everyone. Okay, please don't go away just yet. A couple favors to ask. Favor number one, and I know I've asked before, but if you haven't had a chance to leave a review and you enjoy the show, it would honestly mean a lot if you could go to iTunes and write a review. That goes a long way, so thank you for that. Also, I had a chance to deliver a keynote based on a lot of the learnings I've had from this show. Really enjoyed it. So if you are in any way affiliated with any organization, for-profit, non-for-profit, doesn't really matter, but there's some event where you think they might be looking for a keynote, I appreciate if you would keep me in mind for that. I can be reached at glenn@theartofexcellence.com. Thank you all for listening. We are inching closer to episode 100. Super excited for that sometime later this year. In the meantime, keep being excellent. Tune in next time. Thanks, everybody.